So assignment electric field and capacitor, question number 4. The circuit shown is designed to test reaction time. So the following instructions will test the reaction time of a student. So this circuit can be used to test the reaction time of a student, how it works. What happened, like hide switch S1. So we'll hide the switch S1 from student. Move S1 to a position 1. So we will first place to position 1. This S1 is positioned to place at 1. And then we'll wait until the voltmeter reads 6, because like first it's like a charging. So when we connected here, the capacitor will start to charge. Then we will close the switch S2 and at a random time move S1 to a position 2. So the buzzer sound. Then as soon as the buzzer sound, the student should open S2. So when student here, he should open S2 and use a new voltmeter reading to calculate the student reaction time. How will calculate reaction time? Like we can use a formula V equals V naught. Like we'll use a formula V equals V naught e raised to power minus T over RC. V naught is the maximum voltage, which is 6 here. V is the voltage, like when we close this S2 and the capacitor is discharging, when the student open this S2, what voltage is left in the capacitor, like across the capacitor, that is V2 or V. And R is the resistance of this through which it is, if we can see, like the total resistance of a circuit, including buzzer and the fixed resistor, so that will be R. And C is the capacitance. So using this, we'll find how much time it will take to change a voltage from 6 to, example, 4 volts or 3 volts. And using this, we can determine the time taken by student to react to this, which is also known as the reaction time. Explain how the circuit works to test the reaction time. So as I mentioned, how the circuit is working to test the reaction time. So first, initially, when switch S1 is moved at position 1, the capacitor will charge. Or position 1, when the switch, when S1 at position 1, the capacitor will charges. Then what happened? When S1 is moved to position 2, the capacitor discharge. So capacitors start to discharge or they start to give out the charge. And when S2 is open, the capacitor stop discharging and we can also say the circuit is open. And we can use a formula, like how we can work out the reaction time. So we can use a formula V equals V naught e raised to power minus T over RC. So this formula can be used to work out the discharging time of the capacitor and like how much time the capacitor takes to discharge to change from one value of the voltage to another. In part B, when the circuit is in use with a particular student, the final voltmeter reading is 0.7. The student show that the student reaction time is about 0.2. The capacitance of the resistor and the buzzer, resistor is 338, buzzer is 38, capacitance is 270 microfarad, and the final voltage is 0.7. So 332 and 38. So this is 332. And this one is 38 ohms. So what is the total? So 332 plus 38 which is equals to 370 ohms. That's a total resistance through which capacitor discharging. So we'll use a formula V equals V naught e raised to power minus T over RC. So that is the final voltage at which it stopped discharging is 0.7. Initially started with 6. E raised to power minus T, we don't know. R is the total resistance of a circuit, which is 370. And the capacitance is 270 micros, which is 10 power minus 6. So when we simplify this, the time which will come out as 0.21 seconds. So this is a as they are mentioned that we have to show it's about 0.2 seconds. So remember one thing, when the capacitor is discharging, you have to include all the resistance of a circuit, not only the resistor, like resistance of a fixed resistor or the total resistance of a circuit. Yeah. Then sketch a graph for potential across a capacitor against the time when switches move from position 1 to position 2 and the switch is S2 is closed. So when move from position 1 to position 2, the maximum voltage was 6. Then it starts to discharge and until the capacitor reaches 0.7. So exponential change, but it should not touch the x-axis. Why? Because the voltage across the capacitor is not 0. So exponential change is there, but it should not touch the x-axis. Then we have explain how to make a circuit more sensitive for reaction time of 0.2 seconds. You should refer to the shape of your graph into. Like how we can make this circuit more sensitive for a reaction time of 0.2. So if we want to, because like we want this circuit to decrease the voltage in this 0.2 seconds. So what we should do, if we want to make a more sensitive, it means we want a greater change in the potential for the same time interval. Because if the potential change is greater, if the change in the potential is greater, it means that we can easily determine this time. So more sensitive refers to a greater change in potential for a given time. So what we should do, if the time constant, the time constant which is a product of R and C, because if you check, the time constant is actually a time taken by capacitor to discharge to 67% of its original value. Sorry, 37% of its original value. Like when it discharged to max 37% of its original value. So when we check, the maximum voltage across the capacitor is 6. What is 37% of 6? So it will be 37 times 6 divided by 100, which is about 2.2 volts. So if we want to determine, like if we want to make it more sensitive, so the reaction time must match with the value for time constant. Otherwise, what might happen if we use the higher, like the time constant, which is a product of R and C. If we have a high value of R and C, the product of R and C will be high, then what might happen? Because like making something sensitive means for a small change in one quantity, the other quantity should have a larger change. And what we are doing, we are measuring a potential difference. In this quantity, we are measuring a potential difference. So we want the potential difference to change greater, but in a small time interval. Like it was 6, if it changes from 6 to 0.2 volt, it will be a greater change as compared to changing from 0.6 to 0.7, from 6 to 0.7 volt. This will be a small change, this will be a greater change. We want the change to be greater. But if we increase the value for a time, if we use a high value of a time constant, then the capacitor, the value for R and C will be very high. If the value of R and C is high, what will happen? The change in the potential will be slow. And if the value of the RC is low, like if we have a small value of RC, then the change in the potential difference will be maybe the capacitor will discharge completely, even the student is not able to change the position of the switch. So we want, like when the student is reacting, like taking about 0.2 second, so we want to, this capacitor, like say initially the switch is open, when the so initially the switch is closed, and when the switch is open, we want to take about, like it is taking about 0.2 seconds. So we want the capacitor to discharge in 0.2 second, but not completely, like still some charge is there. So this time 0.2 second must be equal to RC, the time constant. Because if the value of the capacitance and the resistance is so high that maybe the capacitor will not discharge in this 0.2 second. And if the value of the RC is too low, then the capacitor might discharge completely. So what we want the product of RC should be approximately equal to 0.2 second or approximately equal to reaction time. So still there is some voltage when the switch is open. If the value of the RC, like say the reaction time of a student is taking 0.2 seconds to move the switch from one position to another. If the value of the RC, the time constant, is too high, then what might happen? Maybe the student took 0.2 seconds, but the highest voltage was 6, and when it, after 0.2 second, it might reach 5.95. So it's a very small change is there in the voltage. So it's not a considerable change. It won't be sensitive. Like, because to be sensitive, we want a greater change, but in the same interval. And if the value of the time constant, RC, is low, what might happen? The maximum volt in the same time interval, 0.2 second, when the value of the R and C is low, so initial voltage will be 6, but the final voltage may be 0. Like capacitor might discharge completely. So what we want the value for the time constant or RC should be approximately 0.2 seconds, so that it won't discharge completely. It will still have some charge and it will be more sensitive because it will show a change in the voltage or greater change in voltage. Is it clear, this part, like how we can make it more sensitive? Okay. Then the next part, this was sketching. I think this was the last topic. Then another question is there, question 5. The photograph shows a Van de Graaff generator which is used in school. A dome is there. Like basically what happened, the conveyor belt carry the charge which are transferred to the dome, and this dome will store the charge. In a Van de Graaff generator, the charge is transferred to a hollow metal dome which is insulated from the ground, like it cannot be discharged. The dome may be treated as a positive charge sphere with the charge distributed evenly on the surface. So on the surface, the charge is evenly distributed. And we can consider this dome as a positively charged sphere. Like if there is a sphere and which is a positively charged, so we can consider like this. Remember, because within the hollow sphere, there is no electric field. So only electric field, like if we start from the center and we want to sketch a graph for strength, variation of electric field strength and the distance, we know E is equals to KQ over R square. So it means it is inverse square relation. But within, like the radius, there is no electric field. So electric field will be zero till the radius of the sphere. And then it will be maximum. At this point, it will be maximum. And as we move away, it will follow the inverse square law. So double the distance means electric field strength will decrease by 4. So there will be an exponential, like inverse square relation is there, but don't touch the x-axis as it is changing, but electric field act at an infinite range. So you cannot say electric field will be zero at this point, at any point. So it will be near to the axis, but don't touch the x-axis. So if the first part, electric field is outside the sphere is same as for all the charge concentrated at the center. The diagram shows a strength of like electric field of a positively charged conducting sphere suggests why there is no field lines inside the sphere. So why there are no field lines is because the resultant force on the charge would be zero. Like for example, if there is a charge here and a positive charge here, like charges repel each other. Or if there's a negative charge here, unlike charges attract. So if one positive from here and one positive from here, because they will apply the same force but in opposite direction, so there will be force, but the resultant force is zero. If the resultant force is zero, that's why there is no electric field. So we don't represent by the line. If there is a force of 10 Newton towards right, a force of 10 Newton towards left, so the result is zero. So why there is no electric field lines between the sphere? The answer is as there is no resultant force within the sphere, or there's, you can also mention there is no charge inside the sphere, so that's also a reason for electric field line. There are no electric field lines. Then we have a sketch. So again, we'll sketch accordingly. Inverse square relation. So it will, like if distance double, electric field decrease by 4. Distance 3 times, electric field decrease by 9. Distance 4 times, electric field decrease by 16 times, and so on. The capacitance of a sphere of radius r is given by a formula 4 pi epsilon and r. The dome of a Van de Graaff generator behave as a conducting sphere of radius 12 centimeter. The charge on the dome is this. Calculate the potential difference between the dome and the earth. So we want to calculate the potential difference between the dome and the earth. So like we want to calculate the voltage. And we consider the voltage of the earth, like earth is ground or zero is there. So we'll use a formula of like Q is equals to CV. So V is equals to Q divided by C, where Q is a charge on the dome. So charge on the dome is 1.5 into 10 to the power minus 6 divided by the capacitance. So what is the capacitance? How to work out? We have the formula C is equals, they mentioned here C is equals to 4 pi epsilon R. That is the formula for capacitance of the dome. So 4 pi epsilon R. 4 is constant, pi is also constant 3.14, epsilon 8 point, value of the k is 9 exponent 9. For epsilon, you can check the last part of the exam sheet, but it is like 8.85 into 10 to the power minus 12. And R is a distance, which is the radius, which is because 12 centimeter dimensions, so 0.12. So when we substitute, this will give us the capacitance. Which is 1.33 into 10 to the power minus 11. That's in farad. And then 1.33 into 10 to the power minus 11 Q divided by C. So this will give us about 1.1 into 10 to the power 5, which is a very high voltage. In part B2, the dome of the Van de Graaff generator is connected to earth through a resistor R. Calculate the time for a Van de Graaff generator to lose 70% of its charge. So maximum voltage we have in the previous, like the Van de Graaff, the dome of the Van de Graaff generator, maximum voltage was 1.1 into 10 to the power 5 volts. We want it to lose 70% of its charge or to decrease 70% of its original value, or the maximum charge on the dome. In the beginning, the total charge which was stored there on the dome was 1.5 into 10 to the power minus 6. So we can use a formula V is equal, or you can also use a formula V is equals to V naught e raised to power T over RC, or you can use Q is equals to Q naught e raised to power minus T over RC. So we want to determine a time taken by Van de Graaff to lose 70% of the charge. So we have the formula Q is equals to Q naught e raised to power minus T over RC. If 70% of the charge is lost, this Q is not the charge. This Q is not the charge which is lost. This Q is the charge which is left on the capacitor. So how much is left if 70% is lost? So 30% will be left, or 30% will be equal to 0.3. So 30% of Q naught will be there, and this is already Q naught e raised to power minus T over R, which is 9.11 into 10 to the power 11, and C is the capacitance which we calculated in the previous part, which was 1.33 into 10 to the power minus 11. So this Q naught will cancel with Q naught. 30% means like 0.3, because 30 divided by 100. So 0.3 is equals to e raised to power. So we'll take ln both sides, log both sides. So this will be ln 0.3. ln will cancel with e, so it will be minus t divided by 9.11 into 10 to the power 11 into 1.33 into 10 to the power minus 11. And then when we take ln of this will also give negative, so minus will cancel with minus, and this all will go there in multiplication. So the time it will take, which is about 14.6 seconds to discharge. So that is the time taken by this Van de Graaff generator to discharge. And in question 6, a teacher states that the repulsive force between 1 coulomb charge on the ground and 1 coulomb of a charge on 1000 mass is large enough to support the mass when they are 1 kilometer above the ground. Determine whether the teacher is correct. So, like we have 2 charges are there, which are 1 coulomb charge on the ground and 1 coulomb charge on a 1000 kilogram mass. Is large enough to support the mass. So like this object is there, this is having a mass of 1000 kilogram. So they are saying that, and there's a repulsive force, so both are repelling each other. So this electrostatic repulsion is more than the weight, or more than, or it should be equal to weight, so it can support. So first what we'll find the force between the charges. F is equals to K Q1 Q2 over r square. And when it is 1 kilometer above the ground, means the distance between the charges, that's 1 kilometer or 1000 meters. So F is equals to K Q1 Q2 over R square. K, the value of the K is 9 exponent 9. The value of the charge, 1 coulomb, and so it will be 1 and 1, and the distance between them is about 1000, so it will be 1000 square. So when we substitute, this will be like, because it will be 10 power 6, so this will be 9000 will be there, or 9 exponent 3 will be there. So 9 exponent 3 Newton is, or 8 K, value of the K is actually 8.99. So if it is 8.99, it will be 8.9 exponent 3 Newton, or 8900 Newton will be there. That's a repulsive force, 8900 Newton. And what about the weight? Weight is mass multiplied by gravity. The mass of this is placed on 1000 kilogram, and the gravity is 9.81. So when we substitute, so 1000 multiplied by 9.81, so it will be 9810 Newton. So here weight is 9810, which is more than the repulsive force. So this cannot support. Like at a distance of 1 kilometer, it cannot support. It may support a distance less than 1 kilometer, but not at a distance of. So the statement is basically the force is like cannot support the repulsive force, the electrostatic force, or a force between the charges is not sufficient to balance 1000 Newton to balance a mass of 1000 kilogram at a distance of 1 kilometer or 1000 meters. It can be less than, may be supported, but not to a distance of 1 kilometer. So that we will write that the force is, electrostatic force is not sufficient to balance the not sufficient or enough to support weight of one or a mass of, because I'm using a mass of 1000 kilogram at distance of 1000 meters or 1 kilometer. Is it clear discussion that how we worked out that whether the weight is sufficient or not? So this is exercise assignment related to electric field and capacitor. So there are about, you have it is important part, about 23 questions are there. 6 of them I have solved today. Remaining tomorrow we will solve like about 5 to 6 questions. The remaining you will solve by yourself.